Hi, in this video, we want to take a look at robust regression techniques. All right, so the big idea here is that we want to do a linear regression model, but there's a problem. The assumptions of linear regression are not met by our data. So what can we do? Well, we could still build the model knowing that there's problems. Might not be the best choice. Or we could pull out robust regression techniques. So here, this is a good thing to have in our tool belt for when we need it. Now, a good question that could come up is like, why don't we just always use robust regression? Well, it works out that if the assumptions of regression are met, we have really more oomph in our model if we use the theoretical aspects that are present. And so if we want as much oomph as possible, we want to exploit all the aspects of our data. So we would prefer to use linear regression if we can. But if we can't, we bounce to robust techniques and life is good. All right, so robust regression is an area of statistical analysis that caters to like outliers and observations that deviate from like our theoretical assumptions about our model. A traditional regression technique such as ordinary least squares performs very well when the assumptions of constant variance and normally distributed residuals are met. However, a lot of times in real life, these assumptions don't hold. Anomalies and outliers can disproportionately affect the estimates of our regression parameters, leading to inaccurate predictions and problematic models. This is where robust regression comes in handy. So robust regression methods are designed to not be overly affected by violations of those assumptions. Now, they're not 100% bulletproof, but they're resistant to the problems. All right, so let's go ahead and first, we're going to take a look at regular ordinary least squares just to kind of benchmark ourselves from where we're at. So in ordinary least squares, we're going to build a linear model. And the example I'm going to do over and over and over in this video is miles per gallon depends on weight. So we're going to do regular linear regression, so ordinary least squares. What I'm going to do is I'm going to have the computer find the intercept and the slope that minimizes the difference between my observed and my modeled values. My model is going to be a straight line equation, y equals mx plus b, just like you had in middle school. So observed minus model value, which comes from y equals mx plus b. Do the subtraction, square it, add them all up. I want the intercept and the slope that minimizes the difference squared added up. Now, if I have more predictor variables, I can throw them in conceptually. It really doesn't make a big difference for the purpose of this video. I'm just going to keep it simple to make it as accessible as possible, where we just have one predictor every single time. All right, so when I do this, I've got my formula, miles per gallon depends on weight. My data, I'm using the MT cars data set in R. And when I fit it, this says that about 37 is my intercept and negative 5.3 is my slope. So as weight goes up, miles per gallon goes down. And, we get some output on, model quality, statistical significance coming over here with the p-values. And we have a representation of our residuals using the box plot values. Now, when we have linear regression, the mean of our residuals is always equal to 0. Residuals always add up to 0 by the structure of regression, how we built it up mathematically. Now, robust regression techniques, I'm going to talk about 3 of them. Now, there are others, but these are like the heavy hitters in it, so I'm just going to focus on these. So the first one is going to be M estimation. So this is a generalized form of maximum likelihood estimation that allows heavier tails. This minimizes the sum of a function of the absolute residuals. And so in R, we can use the mass package. It's R robust LM or our robust linear model. All right, so I've already loaded the mass package, and it's RLM. And then you'll notice that it looks a lot like regular LM like notation. Boom, I've got it. And so now, things are pretty similar, but you'll notice there is a difference. There is a slight difference here. That's not too surprising. So a lot of times, like if the violation is not too severe on the assumptions, ordinary least squares and robust techniques will pull up pretty similar models. Not exactly the same, but they'll be in the same ballpark of each other, which we're seeing here. Now for least trim squares, what we're going to do is that we're going to minimize the sum of the smallest squared residuals. So what we're going to do, we're going to really just focus on a subset of our data where we're going to focus on the smallest residuals, and we're not going to really worry about the bigger residual values. We're going to treat those as outliers. In fact, we can go, we can get to like almost half of our data can get kicked out in this technique. And so since I'm kicking out the ones that are pulling away from everybody else, this technique is resistant to outliers. And the robust base package, this package has a lot of robust statistics functions in there. It stands for basic robust statistics. And LTS regression is our function for this one. Once again, this looks a lot like the way that we run linear models. And you'll notice that the output visually is very similar also. Now we do get a little bit different of an estimate for the intercept and the slope, but everything else looks pretty similar. Now for MM estimation, this combines the advantage of M estimators and S estimators. This is another robust estimator. I'm not going to talk about it in this video. In essence, MM estimation applies an M estimation to a rescaled version of the data sets. MM estimation is more efficient than regular M estimation, and it also is robust to outliers. You can perform MM estimation using the robust base package once again, but this time it's linear model robust. All right. And you will notice that once again, it's pretty similar usage to what we had before. Now there's a little bit of difference in what gets spit out, but we can see that it's the beginning is very similar to what we've had before in the other models. Now when we get down to here, things there's a lot more going on. And these are aspects of what was going on when it was actually fitted. Something I want to point out is when we talk about number of iterations, if your number of iterations is large, frequently that's an indication that you have a bad model data combination, that your model really doesn't fit your data very well. So if it takes a lot of iterations to converge, you might want to consider a different model. I haven't seen that written down anywhere. This is from personal experience of building models, waiting for it to spit out, and then being like, hey, wow, this is a crap model. All right, so let's talk about the assumptions of ordinary least squares. And so these assumptions, when these are violated, we want to use a different tool than regular least squares. All right, so the first assumption of ordinary least squares is that we have linearity going on. That's just saying that our math equation is right, that we are choosing the right math equation to connect our predictor variables to our target variables. If this is not the case, I need to choose a different form of model, maybe something like Loess or generalized additive models, maybe a decision tree, some other form of modeling, depending on what my project is. All right, and so how we want to check this frequently is that if I only have one predictor variable, I plot my predictor variable on the x-axis, my target variable on the y-axis, and I look and see. Now, when I have more variables, more predictor variables, I can repeat this over and over, definitely useful. And I can also plot predicted values on the horizontal axis and target values on the vertical axis. And if everything goes well, ideally, we would see a line y equals mx ish look in line with the dots. So here I feel like there is a there is a linear relationship possibly. Now, our next assumption is independence. The independence assumption states that the residuals, as the errors, are independent of each other. And so notice that the actual observations themselves do not have to be independent of each other, but the errors do. So that's something different. So if I'm changing my X value systematically in my sampling scheme for like let's say a scientific experiment, that's okay. The X values are not independent of each other. If I'm running an experiment, I set the value of X, I turn it up one notch, run the experiment, turn it up one notch, run the experiment over and over and over. That doesn't violate the linear regression assumption. Now, probably better if we had a randomized system, but this is good. From a linear regression point of view, we don't worry about it. So the residuals from one prediction need to have no influence on the residual on another prediction. This assumption is crucial in time series data where observations can be correlated in time. And so one thing we can do, if you take a look at things from a time series point of view, we can test to see if there's an autocorrelation. Frequently, we're going to use a Durbin-Watson test to check for independence in residuals. Now, the next assumption is homoscedasticity. And so here we're saying that with respect to the predictor variables, we have constant variance of our residuals. And so when it's not this way, what can happen frequently is that it'll have like a horn shape or a triangle shape, that a predictor variable on the horizontal axis, I have the y variable on the vertical axis, and it can look like a horn. And when that happens, it looks like a triangle region that, they're all bunched up around one region, and then they're spreading out as the X value increases. That's not constant variance. And so I've seen this in plenty of places in real life with real data. Typically, running a transformation on our data will resolve this issue. All right, so to test for this, for homoscedasticity, we can use either the Bruch-Pagan test or the White test. The White test is a little bit more flexible. It does not make the normal assumption, but different statisticians like both of these. So choose whichever one you're more comfortable with. Choose whichever one your stakeholders are more comfortable with. All right, so now here, let's look at our residuals on the vertical axis by the fitted value. So I have the predicted value on the horizontal axis, and I have the residual on the vertical axis. All right, so in my eyes, right now, just looking at it, I'm tempted to say that there's a U shape. Now, here's a good rule of thumb when you look at these plots. If I was to move, add, or delete one point, and it would stop me from reaching the conclusion, my conclusion is wrong. So let's say I think, hey, this has a U shape. If I was to take this point right here and move it there, then honestly, I wouldn't see a U shape anymore, because part of the U would be gone up top here and it would disrupt it on the left. So if you can move one point and come up with a different conclusion, you don't see anything. But humans are really good at finding patterns, even patterns that aren't there. So just watch out for that. Now, the last one we want to check is normality. All right, so when we check normality, we have QQ plots, we have histograms to visually check. We can also run hypothesis testing, such as the KS test or Shapiro-Wilk. Shapiro-Wilk is very sensitive. For large data sets, it's almost guaranteed to reject the null hypothesis and conclude that you do not have normality. Typically, most of the time, we just kind of eyeball it. We take a look at the histogram or the QQ plot. Here, there isn't that much data, so I feel like I can't conclude that's normal or not. It might not be normal, but honestly, such a light data set, I don't feel like I can reach a strong conclusion. Now, no multicollinearity. This is important when I have more than one predictor variable for multicollinearity, we're worried about having correlated predictors, or when I have multiple predictor variables that cumulatively can be correlated with another. Typically, we use variance inflation factor to detect this, and multicollinearity can absolutely wreck your model. How we deal with this is basically by removing predictor variables that we don't want to have in there. Now, if another tactic for dealing with this would be to run ridge or lasso regression. If we have predictor variables that we want to kick out that are redundant, or if we could use ridge regression when there are predictor variables we have to keep in, but we see that there's a problem with multicollinearity. All right, so that we just talked about the assumptions of linear regression. So now let's talk about when to use robust regression instead of standard linear regression. So all the things I just talked about a moment ago are things that have to hold for linear regression to be the right model. Now I want, so if something is wrong up above, you need to use a different model. You need to take a different approach. You need to adjust something. Here, I want to talk about the signals for when you use robust regression in particular. All right, so I'm going to use robust regression when we have outliers or anomalies in my data set. We have homoscedasticity, and typically I prefer to try transformations to deal with violations of homoscedasticity, but it doesn't always work out. If it doesn't work out, then I'll go to robust regression. And then non-normality of the errors, when this occurs, then we can bounce to robust regression. And so here we're just running through a few models, just showing you how it's done. So here I've got my ordinary least squares. Here I've got my robust regression. And we can see that a lot of times we end up getting similar coefficients when the violations are not severely violated. So our robust regression methods are M estimation, which is a maximum likelihood estimator. We are minimizing the sum of the function of absolute residuals. And this method provides a robust alternative to least squares regression by reducing the impact of outliers. All right, so what this does is that instead of squaring the difference between model and observed, I'm going to take the absolute value of modeled and observed, and I'm going to change the power, or it doesn't have to be an exponent, but I have to have a non-negative function I'm adding up. I can tweak it so that outliers don't have as much of influence. So when I have a number bigger than 1, like 2, 3, 4, 5, when I square it, I get back a bigger number. When I have a number that is between 0 and 1, and less than 1 and greater than 0, and I square it, I get back a smaller number. So what this does is that squaring gives us a bigger number. That means that squaring of the error, if I have a larger error, that means the squaring makes it even bigger in magnitude. And when I'm doing that minimization approach, that one point is going to pull the rest of the model towards it. And so this technique works to minimize the impact of those large deviating values. Now, least trim squares. So what this does, this works to make sure that we have a high breakdown point. I'll talk about breakdown point in a moment. And so we're going to minimize the sum of the smallest squared residuals. And so I'm only going to worry about my smallest residuals. I'm going to ignore the rest of my data, and I'm going to fit where the residuals are small. So effectively, I'm saying, hey, for my model, what are the outliers? Ignore those guys. MM estimation, this is going to combine the robustness of M estimators, maximum likelihood, and high breakdown point of S estimators. MM estimators are more efficient than M estimators, and they're robust to outliers. And so, we're going to use robust base to perform this. And notice that I get a lot more output on this one. Now, theoretical background of robust regression. So the first one I want to talk about is the breakdown point. An important concept in robust regression is the breakdown point. The breakdown point of an estimator is the smallest proportion of incorrect observations that can cause the estimator to take an arbitrarily large value. The larger the breakdown point of an estimator, the more robust it is. So what we're saying here, let's say I throw in a polluted, grossly bad value into my data. If it doesn't impact the estimator, then I have a more robust situation. So the breakdown point is how much crap data could I throw in before I get a bad estimation, or I should say polluted estimation. Now, ordinary least squares, for example, has a breakdown point of 0, has a breakdown point of 0, which means that one single outlier can substantially affect the regression estimates. In contrast, robust regression techniques have higher breakdown points. For example, that least trim squares estimator, we can have the breakdown point at 0.5. I can work with just half my data and run with it. And so this means that we can have like bad polluted data in there up to half of our data sets. I mean, that's kind of powerful. It's kind of shocking. Now, when I'm dealing with M estimators, this is going to be a maximum likelihood estimation. And how we're going to approach this is that I'm going to take my modeled value, I'm going to take my observed value, subtract them, and then I'm going to have some non-negative function that I'm going to apply. So what I could do is I could take the absolute value and then square it. Absolute value and square it. This would be the same if rho was absolute value then square. That would be the same as ordinary least squares. What I could also do as an alternative, I could take absolute value and cube it. Now, if I was to cube it, I would have an even bigger impact of outliers. And that, in that situation, minimizing a cube, a value greater than 1 would be even bigger if it's cubed, or power 4, power 5. So that means that the model would be fitting mainly to like the outliers and less to the regular data. So what we could do is we could reduce the power. Instead of 2, we could go with a power of 1, really no exponent, a power of 1/2, 1/4, anything that we choose. And then we're going to find the parameters that minimize this. Now, for least trim squares, how we achieve this high breakdown point is that we're just ignoring, a large portion of our data. And so as long as our polluted data is in the ignored part, it's not, our model will be independent of the pollution. And MM estimators combine M estimators and the high breakdown points of S estimators. And so this is achieved by doing an M estimation step of the residuals that have been rescaled by an estimate of the scale obtained by an initial S step. So this makes MM estimators more efficient than M estimators while maintaining the robustness to outliers. So robust regression techniques are an essential tool for handling outliers and other violations of the assumptions for standard regression methods. They offer a suite of methods designed to reduce the influence of outliers and anomaly on our model fit, thus providing more reliable and accurate parameter estimates. The M estimator, least trim squares, and MM estimator are all robust regression methods that can be easily implemented in R using the mass or robust base packages. However, these methods are not without their own assumptions and conditions, and the choice between these methods and others should be guided by the nature of the data and the objective of our analysis. Now, keep in mind, no method is a one-size-fits-all. We need to always use a deep understanding of our data and the objectives of our analysis and the strengths and weaknesses of the available methods when we make our choice. And here are the homework problems. All right, well, that's all I've got for you. Life is short. Do math.